So hello everyone. Uh, hello. Today we're going to take a look at a very important concept in pharmacology, general pharmacology to be exact, and that is difference between order of kinetics, first order kinetics and zero order kinetics. Sorry, this should be zero order kinetics, right? It is an important question, very important question that comes in prof, especially prof written exams multiple times. But it's a question that I frankly struggle with because a lot of students, including myself, have a hard time understanding the actual meaning behind first order and zero order kinetics. So what we tend to do is we try to mug up these things, right? Try to memorize it without understanding. So if you try to memorize it and we forget it and we try to memorize it again. So I believe is if you understand it, it's a lot easier to memorize. So in this video, we'll try to understand the difference between first order and zero order kinetics. Okay, so let's just get right into it. Quick note before I start, if you want my pharmacology, microbiology, or pathology notes for prof, as you can see, I have a lot of notes covering every single topic that you need to ace your prof written exams. You can contact me via my website where I have given my WhatsApp number, right? You can always contact me. So with that out of the way, if you so let's just get right into it. So first order kinetics, F per fraction, right? So in first order kinetics, constant fraction or percentage of the drug is eliminated per unit time, right? Whereas in zero order kinetic, constant amount of drug is eliminated during per unit time, right? So what do I mean by that? So constant percentage means in 1 hour, right? If it's a metabolism of first order drug, in 1 hour, say 50% of the drug is eliminated. For example, if the drug had 100 milligram in the plasma, in 1 hour it will be 50 milligram, and in second hour it's going to be 25 milligram. In third hour it's going to be 12.5 milligram, because in every hour, in every per unit time, we're removing a constant percentage, 50%. So 50% in shit, there's no electricity. All right. So 50% in hour one, so from 100 to 50, and then from 50 to 25. So in second hour we remove 50%. So in each hour we are removing constant fraction, that each hour we are removing 50% of the in each hour we are removing 50% of the drug. That is why the fraction is constant, 50% is constant, right? But in zero order kinetics, constant amount of drug is removed. So for example, in each hour, 20 milligrams of the drug is removed. So for example, if there is 100 milligram of blood drug in the plasma, in first, after 1 hour there's going to be 80 milligram. After 2 hours it's going to be 80 minus 20, 60 milligram. After 3 hours it's going to be 80 minus 20 again, because it's constant, is going to be 40 milligram. So in zero order kinetics, constant amount of the drug is removed, whereas in first order kinetic, constant percentage of the drug is removed. This is the most basic concept. So I'll go over it very quickly again. In first order kinetics, 100 milligram drug, in 1 hour it's going to be 50, in 2 hours it's going to be 25, because we're removing 50% of 100 is 50, right? And then 50% of 50 is 25, right? So we're removing constant fraction of the drug every single hour, right? But in zero order kinetics, we're removing constant amount. So in every hour, not percentage, fixed amount of the drug is removed. For example, 20 milligram. So if 100 milligram drug, in 1 hour it's going to be 80. In after 2 hours it's going to be 80 minus 20, 60 milligram, right? So constant fraction and constant amount, F for fraction, right? Just a mnemonic to help you remember. Now, if you draw the graph, right? So this is what I got from the internet. It helps you it helps to do understand it better. So if you draw a graph of a first order elimination kinetic, right? The graph will go like this, right? It's going to be an exponential graph. I don't know if it's called exponential. It's going to be a curve, right? So what do we mean here? On the y-axis we have the amount of drug, and in the x-axis we have the time. The same here, in the zero order kinetics, right? The same thing is happening here. So we know that in first order kinetics, constant fraction of drug is removed, right? So when you plot this, when you trace the amount of drug according to the time, how much drug is remaining in the plasma, if you in 1 hour, 2 hour, 3 hour, right? The graph will be like this. In first order, in the fraction one, it will be curved. But in zero order kinetics, the graph will be something like just a second, let me fix my camera. All right. So in zero order kinetics, the graph will be straight. It will be a linear graph, right? It will be a linear graph. So I'll explain why. Because the second point, so the graph is in first order, it is exponential. In the zero order, it is linear, it is straight, and this one is curved, right? I'll explain why this is curved and why this is straight in a minute. Now let's go to the third point, right? The rate of elimination is directly proportional to the concentration of drug in plasma in first order kinetics, whereas the rate of elimination is constant regardless of the concentration of drug in the plasma, right? So what do we mean by this? Since in first order kinetics, as I told you, the fraction is constant. So for example, in the example, 100 milligrams in 1 hour, 50% is gone. So we remove 50 milligram. So it's gonna be 50 milligram in 1 hour, right? But if the drug was, for example, 200 milligram, so if it, in first order kinetics, sorry, in first order kinetics, if the drug was 200 milligram, still we are also, in this case also, we are removing 50% in first 1 hour, right? So from 200 milligram, it's going to be 100 milligram. But so in this case, in the first case, if we give 100 milligram, then we remove 50 milligrams, right, in 1 hour. But if we give 200 milligrams of the drug, we remove 100 milligrams in 1 hour, because we are removing the percentage, right? So 50% of 200 milligram is going to be 100 milligrams. So as we increase the amount of the drug, so for example, if there is if the drug is 1000 milligrams, what's 50% of 5000 milligrams? That's 500, right? So as we increase the amount of drug in first order kinetics, right, the amount of excretion is also increased, or the rate of elimination is also increased when you increase the amount of drug. As I give you example, in 100 milligrams, it's going to be 50 milligrams is excreted in first hour. If you give 200 milligrams, 100 milligrams will be excreted. If you give 1000 milligrams of the drug, because 50%, we're excreting 50%, right? So 500 milligrams will be excreted, right? Are you getting me? I hope you are getting me. I can't talk to you. So that's why the rate of elimination, the more the amount of the drug, the more drug is getting excreted, because it's a percentage, right? But in second order in zero order kinetics, sorry, there is the rate of elimination is constant regardless of the concentration of the drug. So for example, because why? Because we are removing a constant amount, not fraction, right? So if you give 100 in zero order kinetics, if you give 100 milligrams of the drug in 1 hour, it's going to be 80 milligrams, because we are removing 20 milligrams, right? But if you give 200 milligrams of a drug in zero order kinetics, in 1 hour, it's going to be 180 milligrams, because here we are not looking at the percentage. We're not removing 50%, right? We're removing fixed amount. So if you give 1000 milligrams of the drug as well, only constant amount, it's only going to get removed 20, only 20 milligram is going to be removed. So if you give in zero order kinetics, if 100 milligram drugs is given in 1 hour, it's going to be 80 milligrams. If you give 200 milligrams of the same drug in 1 hour, still constant amount is getting removed, so the amount is still 20 milligrams, so it's going to be 180 milligrams. So is the rate of elimination increasing when you increase the drug concentration, or the amount of drug? No, right? Because here, no, because regardless of the drug is 100 milligrams or 200 or 1000 milligrams, we are always removing only 20 milligrams. So the rate of elimination, the amount of drug eliminated per in 1 hour, is always going to be 20 milligrams. So that is that. So that is the second most important difference, right? Now from this we can explain the shape of this graphs, right? So if you know anything about mathematics, right, the slope, this thing, the slope, right, this, so the slope, the slant slope of the curve, the slope of these two curves, these represent the rate of elimination of the curve, right? The more steep the curve is, the more the rate of elimination, right? So in first order kinetics, if you can see here, okay, now let's go to the zero order kinetics first. So what we know about zero order kinetics, what we just discussed, the rate of elimination is constant, right? Because in every hour, we are, no matter the amount of drug, we're removing 20 milligrams, right? So rate of elimination is constant. So the slope should also be constant, because the slope represents the rate of elimination. That's why the graph for zero order kinetics, it is a linear, it's a straight graph, because the curve, the slope is constant. Here there is a single slope, right? So there is no change in the slope, so the rate is constant. That's why it has a linear curve, right? But in zero order kinetics, if you look, right, we know that in zero order kinetics, the rate of elimination is directly proportional to the concentration of drug. So as we increase the amount of drug or the concentration of drug, right, as we increase the concentration of drug, the rate of elimination or the slope should also increase, right? So here, when the drug amount is very high, look at the slope, right? This is mathematics. It's very interesting. Look at the slope. It is very steep. But when the concentration of drug is a little bit less, right? From 100 milligrams, it went to 50 milligrams. Look at the slope. Is it a little bit less steep? For at first, it was like this, right? Because the rate of elimination was very high when the amount of drug was very high. When the amount of drug went to 50%, the rate of elimination became like this, right? And as you see, when the amount of drug reduces further, the rate of the slope is going to get even less. That is why in first order kinetics, the graph is exponential, because the rate of elimination or the slope of the curve is not constant like in zero order. In first order, the slope of the curve is like this because the rate of elimination changes with the proportionate or the amount of drug. So as the amount of drug is decreasing, the slope is also changing. That's why the first order kinetic is exponential curve, whereas zero order kinetics is linear curve. Let me just check if I'm recording. All right. So we discussed that. So from this, we also understand. See, these points are related. When you understand one, you understand another. So from this, that is why it has an exponential graph in first order kinetics, right? Because the rate of elimination increases, it's proportional to the amount of drug. But since the rate of elimination is constant, so the slope is also constant. That's why it has a linear graph. So you can remember this easily, right? Now, let's go to this point. Let's go to the half-life. So the half-life in first order kinetic remains constant, right? So what do you mean by half-life? Half-life means the amount of time taken by the drug to reduce its concentration by half, right? So if for the time taken for 50 milligrams to get to 50 milligram drug to get to half its original concentration, to 100 milligram drug to get to 50 milligram drug. So amount of time taken for a drug to reduce its concentration in plasma by half is known as half-life, right? So what are we saying? The half-life is constant in first order kinetics, but the half-life decreases with time in second order kinetics. So half-life is constant in first order kinetics, but half-life is not constant in zero order kinetics, right? Why? Again, the answer lies in the graph. So if you understand the graph, then only you can understand the concept. So in first order kinetics, this is the graph, and I've explained why is the graph like this. So see, this is a very interesting thing. So we know half-life is the amount of time taken by the drug to reduce to its half its concentration, right? So this is 100 milligrams, right? Now this is 50 milligrams, this is 25 milligrams. So at each point, we're decreasing the concentration of drug by half. So look at how much time the drug is taking in first order kinetics to reduce it to its 50%, by reduce its concentration by 50%, right? So to go from 100 milligrams to 50 milligrams, at time zero it was 100 milligrams. At time to at 50 milligrams, the time is like this. So this is this gap between time zero and it took this much time. It took this much time, right? It took this much time to for this drug to reduce to its half of this original concentration. This is the first half-life, right? This is the first half-life. So again, from 50 milligrams to go to 25 milligrams, look at how much time it took. It took this much time, right? So this is the second half-life, right? So look at the length of this curve, right? It starts from here, to be exact, right? So look at this. Look at the green boxes. This box and this box, they have approximately similar size, right? They are approximately equal, right? So the half-life equal, right? The half-life is, when you look at this graph, time taken, the first half-life and then second half-life, they have the same width, right? So the half-life is constant, right? It's gonna be the same when you go from 25 milligrams to 12.5 milligram when you reduce it, right? So it's gonna continue like that. So the half-life is constant, as you can see from this graph, and I've explained in first order kinetics, right? But in zero order kinetics, let's look at what happens to the half-life. So in zero order kinetics, for the drug to go from 100 milligrams to 50 milligrams, it took, so in 100 milligrams, it's time zero, right? Okay, hold on. It's time here, zero, right? In order, by the time it goes to 50 milligram here, it takes this much time. So this is the first half-life. It took this much time, right? This is the first half-life, right? Now, in order to go from 50 milligram to 25 milligram, it only took this much time, right? So let's compare. This is the second half-life, right? So now let's compare these boxes, right? The first half-life is this big, right? But the second half-life is only this much. So is the half-life constant here in zero order kinetics? No, as you can literally see in the graph. But in first order kinetics, the half-life is constant because this box and this box are the same, right? So that is why in zero order, and then the half-life is decreasing. So as the concentration of drug is decreasing, as the concentration of drug is going down, right, as it is going down, right, the half-life is getting shorter and shorter, because at first the first half was like big like this, right? In the second half-life it became shorter, right? So as you increase the decrease the concentration, the half-life also keeps on getting shorter in zero order kinetics. So that is another difference. Now if you understand the graphs, you can understand this. So that is that constant half-life is constant, half-life is not constant in zero order kinetics. Now easy question, easy point. It is more common. So most drugs in the market, they follow zero order kinetics, and very few drugs follow they follow first order kinetics, and very few drugs they follow zero order kinetics. Okay, so that is important in examples, because if they ask you examples, you can give literally any drug that comes to your mind. It's mostly following first order kinetics, right? But in zero order kinetics, very few drugs such as phenytoin, warfarin, theophylline, you just have to remember the examples of these, right? These drugs, they follow like zero order kinetics, right? My tip would be just remember the zero order kinetics ones, and remaining all the drugs just you can say as first order kinetics, right? It's just more logical to remember like that. Now let's go to the second last point, chance of toxicity. So in first order kinetics, there is less chance of toxicity, right? There is less chance of toxicity. Why? Because you might come up with the answer by this time, right? Because we know that if you in first order kinetics, if the amount of drug is high, the rate of elimination is also high, right? So if there is overdose, right? If I take 500 milligrams of paracetamol, 500 milligram is a normal dose, right? Anyways, if I take 500 milligrams of if I take 500 milligrams of any drug, which is a toxic dose, right? So, okay, let me get a better example. So, if a normal dose of a drug was 100 milligrams, right? But instead, I took 500 milligrams of that drug. That is very toxic dose, right? That can kill you. But if the drug is following first order kinetics, what will happen? So, if the drug is following first order kinetics, what will happen? In first order kinetics, if I take 100 milligrams in 1 hour, the body will excrete 50 milligrams, 50%, right? But if I take 500 milligrams, the body will excrete more amount of the drug, right? The rate of excretion also increases. So in 1 hour, it goes from 500 to 250. So if there is a poisoning case of first order kinetics, the body's excretion rate also increases with the amount of drug, right? So body can quickly excrete the drug. But if the drug is zero order kinetics, if I take 500 milligrams of the same drug in zero order kinetics, right, in 1 hour the body excretes it from a 1 hour, it goes from 500 not to 250. In first order, it went from the toxic drug went from 500 to 250, right? But in zero order kinetics, the toxic drug will go from 500 to 480, because remember the rate of elimination is constant, regardless if you give 100 milligrams or 500 milligrams, is constant. So in 1 hour, it's only going to excrete 20 milligrams of the drug, right? So from 500, it's going to be 480. Instead, in 2 hours, it's going to be 460, right? So the body will very slowly excrete the drug. So in what do we want in poisoning cases? We want to excrete the drug faster, right? That's why poisoning cases or toxicity cases in first order elimination drug is less common, less chance of toxicity, because the body can excrete it. As you increase the toxic dose, the excretion is also increasing, so body quickly gets rid of the drug. But there is more chances of toxicity in zero order, because the body excretes the drug very slowly, because the amount of the rate of elimination does not increase with the amount of drug given, right? I hope I can make that thing clear. And but last but not the least, right, And last but not the least, right? So last point is enzymes are not saturated and enzymes are saturated, right? So enzymes are not saturated in first order kinetics. Okay, so why enzymes are not saturated? This is a, I mean, I can get into it. Okay, we'll discuss this. So why first order kinetics is happening? First order kinetics is happening because the enzymes, what is happening in first order kinetics, as you increase the amount of drug, more elimination is happening. So 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 enzymes are not saturated because there are excess enzymes. When you increase the amount of drug, you can, more enzymes are available to work on that on that drug. So when you increase the amount of drug, more excretion is happening because there are excess, there are like more enzymes that can work. But the rate of elimination does not increase with the concentration of drug in zero order because the enzymes are what? The enzymes are saturated, right? So reason why the rate of elimination is constant in zero order kinetics is because the enzymes are saturated. So all the drug excretion or metabolism is done by the enzymes mostly present in the liver, right? But in zero order kinetic, all the enzymes are already working at maximum capacity. So these are enzymes, right? So these enzymes, enzyme 1, 2, 3, 4, 5, 6, these are already working at maximum capacity. They are saturated. So whenever, so at maximum capacity, this enzyme can only, they are only able to excrete 20 milligrams, right, of drug, as in the examples. So if you increase the amount of drug, the amount of excretion cannot increase because the enzymes are already working at its maximum capacity. That's why the rate of elimination cannot increase with the concentration of drug, right? But in first order kinetics, the rate of elimination can increase with the proportional with the amount of the drug, because when you increase the amount of the drug, enzymes are not saturated, so they can actually degrade more enzymes, degrade more drug because they are not working at their maximum capacity. So when you increase the amount of the drug, the rate of elimination also increases because there are excess enzyme that can work on it, right? So that is, enzyme saturation is the actual reason why zero order kinetics, the rate of elimination is constant. This is all that you need to know. I tried my best to understand about zero order and first order kinetics, right? Now, this is a very important question. They might ask you about this. This is a very fundamental and basic concept in pharmacology, right? Should know, you should understand this. But then I'm including myself, a lot of students have difficulty understanding. Hopefully this video was useful. So let's look at one another prof question, right? Okay. Regarding this, so this is very important prof question. There is another, yeah, so right after this has come like 4 times in prof already, so you should actually understand it. Another, in pharma they gave a understanding based question, right? You can't just mug this thing up. In pharmacology you got to understand it. Hopefully you will understand it. So why plasma half-life varies when drug elimination follows zero order kinetics, right? I have given the explanation here, right? Because due to enzymes, so all this, why the question is asking why the plasma half-life is not constant in zero order kinetics, and I've given, you can give the explanation that I've already given here, right? It's because due to enzyme saturation, the amount rate of elimination is constant. That's why it follows a linear graph. You can say it follows a linear graph. That's why when you look at the half-life is not constant like the first order kinetics. So when you understand questions, when you understand concept, then you can answer it like this. So my answer was plasma half-life varies due to zero order kinetics because of enzyme saturation. Because here the all the enzymes involved in the metabolism and elimination are already saturated. Hence the rate of elimination of a drug is not proportionate to the dose of the drug. With increased dose, the rates of elimination, so with increasing in dose, the rate of elimination remains constant. That is, and it follows the linear curve. That is why when you look at the plasma half-life, it is not constant. The plasma half-life actually decreases with the decrease in drug concentration, right? So if you understood this concept, you can actually answer prof questions like this. So that is it for today. I hope I could make you understand. I tried my best. So if you want this pharmacology, I have pharmacology notes, microbiology notes, right? I have pharmacology notes, microbiology notes on every single topic in prof, right? So if you want these awesome notes that I've made with a lot of effort, right? These are pharma notes covering all the prof questions. You can visit my website here, betternotes.com. betternotes.framer.ai. The link of this website will be in the description of this video, and you can contact me, right? You can check out these notes here, that which will be helpful for your prof preparation, right? So you can contact me in this number. You can click on this link, and yeah, you can contact me, and if you want these notes, you can get me. I would love to give you these notes, right? So hopefully that video was useful, and until then, see you next time.